In this third lecture concerning a general theory for describing classical elementary spinning particles, we are going to analyze the metric structure of the space of states, of the kinematical state of a most general elementary particle. This metric structure we are going to show of the kinematical space is always a metric Finsler structure. So the kinematical space of any arbitrary mechanical system is always a metric Finsler space. Now, you have seen that the Lagrangian of any mechanical system, when we write the evolution in terms of some arbitrary evolution parameter, is always a homogeneous function of degree 1 of the derivatives of all kinematical variables. Well, then we can expand according to Euler's theorem in terms of these variables in this form. Now, therefore, its square will be homogeneous functions of degree 2 and can also be written in this form. But here, these coefficients are also functions of x dot. Then this is the symmetric tensor is a function of the point x, but also of its tau derivative. Then a metric space, whose metric also depends on the derivatives of the variables, is called a Finsler space. The name is due to Paul Finsler, a German mathematician who in 1988 published a generalization of Riemannian metric spaces by including a metric depending on x dot. It was Elie Cartan in 1934 who published a monography and gave the name to these manifolds, the name of les espaces de Finsler, the name of Finsler spaces, to these metric spaces. You see, let us consider, for instance, the free relativistic point particle of this Lagrangian. If we analyze this Lagrangian in a parametric evolution, we define the L0 as L0 t dot, and we include the t dot here, and we see this homogeneity of the Lagrangian. This is a second degree polynomial, and the square root produces this expansion with capital T and capital R can be obtained in this way. Capital T is minus the energy, capital R is the linear momentum. Now, if as usual, we denote the kinematical variables with x0 to the time, xi the coordinates of the point, and then after scaling the Lagrangian by mc to obtain that the whole Lagrangian has dimensions of length, then taking this second order partial differential equation of the L0 square, we get that the metric of the spacetime, or the kinematical space of the relativistic point particle, is Minkowski metric. Oh, it is clear that this constant Finsler metric can also be interpreted as a constant pseudo-Riemannian metric. But it is a Finsler metric, a constant Finsler metric. Now, this is important to realize because although it looks like a Riemannian metric, it is a Finsler one. And then we are going to see that the variational formulation of mechanics is equivalent to the requirement that the evolution of any Lagrangian system in the kinematical space is a geodesic evolution where the metric of this kinematical space is constructed from the L0. You see, written the action integral in this form, we can write this perhaps with a plus or minus sign here as the integral of L square, which represents this, introducing dt inside is this. So our action integral is equivalent to the length of the path followed by the system from x1 to x2. But this action integral, we don't know if it is maximum or minimum, but L square is definitely positive. So if it is definite positive, the arc length has to be a minimum. So our variational formalism is equivalent to a geodesic statement on the kinematical space, but with respect to the metric constructed from L square. Well, in our case, if we are analyzing an elementary particle, the most general Lagrangian of an elementary particle will be the free Lagrangian and the interacting Lagrangian. But the kinematical space of the whole system is the same. The kinematical space of the total Lagrangian is the kinematical space of the initial system of the elementary particle. Then it implies that the metric constructed from L tilde square is different than the metric constructed from the L0 square. Why? Because the introduction or the interaction Lagrangian modifies the metric of the free elementary particle. This means that every interaction modifies the Finsler metric of any particle. Well, we are used to that. We're used to say, okay, gravity modifies the spacetime metric of the spinless point particle. Well, spinless point particle, the metric is Minkowski metric, and gravity modifies this Minkowski metric and produces a new Riemannian metric. But you see, what is the difference between a Riemannian metric and a Finsler metric? In a Riemannian metric, the distance between 2 points depends on their separation, and of course on the point. But in a Finsler metric, the distance depends of course on their separation, but also on the velocity from going from one point to the other. We can say that a Riemannian metric is static, is a geometric metric. It depends only on the separation between every pair of points. However, the Finsler metric is more kinematical, is more physical, because the length between 2 points is not only a function of the geometrical distance between them, but also depends on the velocity when we go from one point to the other. Now, you see what I mentioned before, that gravity modifies the Minkowski metric. But generally, relativity postulates that this new metric is Riemannian, when it should be Finslerian. Therefore, general relativity is making a restriction to a more general situation for analyzing what gravity is making to the spinless point particle. But in fact, the restriction is twofold. Gravity is producing a twofold restriction because it's equivalent to assume that gravity is only acting on spinless point particles and the metric is Riemannian. But if the metric is Riemannian, it is implied that this velocity dependence must be negligible. Or if you like, this spinless point particle is moving at velocity much lower than c. Now, if we want to assume what gravitation produces in a general relativistic spinning particle, what general relativity has to postulate is that the metric of the whole kinematical space of a relativistic spinning particle has to be modified by gravity. But not only the spacetime submanifold, and that the new metric has to be necessarily a Finsler metric. We have to make a revision of the foundations of general relativity. General relativity has to be redefined in order to construct Finsler metrics from the general first principles. We shall see now that it is the low velocity limit, in the case of the point particle, which transforms general Finsler metric into a Riemannian one. Let us consider the following example: a point particle in a Newtonian potential. Let us assume that we have a point particle mass m under the Newtonian potential of another point mass capital M located at the origin. The Lagrangian which describes the motion of this particle is given by this. In terms of some arbitrary evolution parameters, the new Lagrangian is written in this form, and by rescaling by MC such that the new Lagrangian has dimensions of length will be written in this form. Okay, we shall use this Lagrangian to obtain the metric structure of a space-time, but from the original Lagrangian we obtain the dynamical equations of the point, which are these. By solving these equations, we solve this gravitational problem if a point mass m into the gravitational field of a capital M mass. But because this variational formulation is equivalent to the geodesic formulation constructed from the metric obtained from ln square, the trajectory of the point is also geodesic obtained from this. And this is what we are going to make, but the metric of a space-time constructed from this potential, we take the L square, we take the second order partial derivatives, and is this. It is clearly a Finsler metric. Gamma depends on u is here, here, here. So the whole motion of that point particle is a geodesic with respect to this metric, with respect to this Finsler metric. Nevertheless, in the low velocity limit of this metric, we obtain this Riemannian metric. Of course, there are no velocity terms here. And in fact, if we analyze this term, it's basically the square of this one. If it is negligible, this G00 is in fact the Schwarzschild G00 term of a metric of a point in the gravitational field of a capital M mass. So, general relativity as a theory of gravitation makes a very strong restriction to a more general dynamical situation, which requires that the metric has to be necessarily Finslerian instead of Riemannian. So the new metric produced by gravity has to be a Finsler metric. If we assume that the evolution of an elementary particle, at least locally, space-time, follows a variational formalism. So, if it is a variational formalism, implies that locally the metric is Finslerian, and in a cosmological background, the matching of Finsler metric into a Riemannian metric is quite difficult. I mean, it's almost impossible. So, these features are been analyzed in these papers and in this talk, and the whole formalism is described in this monography and also in these documents of a lecture course I lecture at the University of Basque Country. Now you can contact me at that address. And the next lecture, we shall analyze this important theorem, Noether's theorem, because it is through Noether's theorem that we will describe the fundamental observables of a general relativistic spinning particle, in particular linear momentum, energy, angular momentum, spin, and so on. Thank you very much for your attention.